All right, the point of that is that, yes, it looks like a line, but you have no idea what we're actually looking at. You don't know the window of this. And what I did was I zoomed in on one specific point, and I just kept zooming in and zooming in to the point that my window looks like this. So it's really zoomed in around 1. Okay. And this is actually the graph of, so if I hit zoom 6, you'll see that it's really the graph of y equals x squared. Okay. And we're going to get to the reason and the point of that here as we go through these notes. All right, so certain graphs, specifically those that are differentiable, have a property called local linearity. Okay, local linearity, that's kind of the topic of our notes today. And this means that if you zoom in on a point, a specific point on the graph eventually appears to be a line. Okay, just like I just showed you the graph of y equals x squared, but it appeared to be a line when you first saw it. Okay, and that slope is the slope who has the same slope as the derivative of the tangent line at that point. Okay. All right, use your calculator so you guys can do this or just watch me. It's not as much something new that you're doing in your calculator, but use your calculator to zoom into each graph at the given point. Okay, so if we graph the function 1 plus the square root of x squared plus 0.001, okay, that graph looks like this. And if, oh,
anything.
yeah, I got you. Let me brighten this up a little bit here. Where'd that button go? I think it's floating down. There it is. Let me see here. Turn that off. Try this. How's that? Can you see that?
Yeah, we can.
Okay. All right. So I just graphed that square root function right there. And it certainly looks like an absolute value function. It definitely looks like we come to a sharp point, okay, right in here. Okay. But what we're going to do is we're going to zoom in on the point 0, 1, which is what appears to be this vertex right here. So I'm going to hit zoom, which is at the top. Zoom in, so it's option number 2. And I'm just going to move my cursor, which is currently at 0, 0, and I'm just going to move it up till I get close to the point 0, 1. You're not going to land exactly on 0, 1. Your numbers might not even be the exact same as mine, but here's 0.96, here's 1.29. So I'm just going to stay a little bit below it and zoom in on that by hitting enter. Okay. And then if I hit enter again, it's just going to automatically zoom in on that same exact spot. I don't have to hit zoom in again. And so I zoom in a little bit more. Okay, and then I'm going to zoom in a little bit more. So I just keep zooming in on this point. And now all of a sudden, can you see that it's actually not a sharp point, but it actually does curve there? Okay. And then if you zoomed in again, it's going up a little higher now. It's actually off my screen, so I can't even see it. Okay. My cursor got too low. But the point is, let me zoom out one. See if we see it again. I zoom back in again. Zoom out. Probably went too far now. I can't see it. All right, anyway, the point, okay, there it goes. There it comes back. The point is the more you keep zooming in, the more it's going to look linear to you at that point, okay? So it says right over here off to the side, the function initially appears to have a sharp corner, but after zooming in several times, you see that it is indeed locally linear, okay? And if we kept going, we would see the line, okay? So let me show you that by, let me hit zoom in and show you if I move my cursor up even further towards that point. Okay, we start going like this. Then I hit zoom in again and I get closer to that point. And you start seeing it's starting to see how it's starting to flatten off right here. Okay, and if I kept zooming in, it's certainly going to look like a line at this point. Okay. We're just magnifying it tremendously. Okay. So again, like I said, you just want to see that, okay? So we have this other function here, x cubed plus the cube root of x minus 1 squared over 7. And I'm just going to tell you that, we'll graph it. All right, so let's go back into y equals. We have x cubed plus, then let's get a fraction bar going and get the cube root. That's under math, option 4. The cube root of x minus 1 squared. And that's all over 7. And I'm going to hit zoom 6 because we changed our window in that last one. So we're going to go back to the normal negative 10 to 10 window. And there's the graph right there. Okay. And it says the function initially appears to be locally linear, but it is not. So we're going to zoom in on the point 1, 1. Okay. So this time I'm going to hit zoom in and I'm going to move my cursor to the right until I get close to 1. Let me see if I could clear this up for you guys a little bit, if you see those numbers. All right, so I'm trying to get this x value close to 1. That's at 1.06. Then move my up arrow until my y value is close to 1. And zoom in on that point. Okay, and then I'm going to do it again. Okay, so I'm going to zoom in on the point 1, 1. See if we can get this a little closer to 1, 1 now. Let's try this right here. Kind of lost our point here. Anyway, trying to figure out where that point is. Let me try and zoom in. I lost my zoom. Zoom in on 1, 1 a little bit more. All right, and what you find out on this one is that when we plug 1, 1 into this, okay, we're going to get. Try to look at this. The function appears locally. Okay, I think we zoomed in at a bad spot. I don't think I got it right on 1, 1, even though it looks like it. But it's still curving here. Okay, it's not locally linear. Okay, you can still see that there's a little hump in that. Okay, especially going from here to here. Okay, we don't become a line. All right. Okay, so just wanted to show you that in the calculator. You're not going to be zooming in and, on specific points, but the point of this is algebraically, we're going to actually work through this. Okay, so this next example that I have written down for you here is an actual question from the 2005 AP exam. It was question 5 on the AB exam. Okay, and it gives this graph. It says here you were given a velocity graph modeled by the piecewise linear function. So we got a bunch of piecewise lines. So we got this line, and this line. Okay. And typically, if you're not given a function, when they do some of these questions, they're going to give you lines because you can't find the slope if you're given, say, a curve, right? Unless you know the function. Okay. And here's what one of the questions was on that. There's, of course, like usually 3, 4, 5 parts on any one given question. But they were asked to find v prime of 4 and explain why it does not exist. Okay, so this is the graph of velocity, and they're asking us to find the slope at this point right here. Well, obviously, we come to a sharp turn there. Okay, so therefore, we are not differentiable there. Therefore, it does not exist, right? V prime of 4 will not exist. Okay, later they were asked if the mean value theorem is guaranteed a value of C in the interval 8 to 20. So we're talking on the graph from here to here, okay, such that V prime of C is equal to the average rate of change. So that's the mean value theorem saying slope of the secant is equal to slope of the secant is equal to the slope of the tangent. And the answer is no, because we are not differentiable right here. Even that's not in our interval, but we're not differentiable right here either. Okay, we're not locally linear everywhere in that interval. All right, so big question is, what is this all leading to? And we're going to get there just in a few minutes here. So we have another one here. The function f of x equals, that function is locally linear at x equals 0. Thus, it is differentiable there. What is the equation of the tangent line at 0, 1? So we're just going to do a little review of finding a tangent line, okay? So the two things you need to write the equation of a line are, you need a point, we have a point, and we need a slope, okay? To find the slope at the point 0, 1, we need to find this derivative. So f prime of x is equal to, all right, we have a power rule, but then there's going to be a chain inside, okay, because we got this whole thing inside. So 1/4 times 1 is 1/4 x squared plus 0.0001 raised to the 1/4 minus 1 is negative 3/4. And then the derivative of 0.9 is 0. So obviously this is an ugly function, right? It's 4 over, chain rule, derivative of x squared is 2x. Forgot that chain. So we have 2x in our numerator, and we have 4 times x squared plus 0.0001 to the positive 3/4 in our denominator. Okay, and to find the slope, we're going to plug, at this point, we're going to plug a 0 into this, right? Okay, and when we plug a 0 into this, we are going to get an undefined, or what are we going to get? We're going to get 0 in the numerator, and we're not going to get 0 in the denominator, right? Because 0 squared plus 0.001 is some number. Raise that to the 3/4, multiplied by 4 gives us some number in the denominator, but we have 0 in the numerator. So f prime of 0 is going to be 0. That's our slope. Okay, to write the equation of a line with a slope of 0, it's just a horizontal line. So the equation would be y is equal to 1. All right, so now I'm going to show you if we graph f of x. So let's just go ahead and I'm going to get my other calculator. I'm going to graph f of x here. Okay, f of x is x squared plus point, and how many zeros I got there? 3 zeros and a 1 raised to the 1/4. If you have a TI-83, make sure you're putting parentheses around your 1/4 because it doesn't raise that up in the air. And then, or you could just put raised to the 0.25, might be easier, plus 0.9. All right, we're going to graph that function, which again appears to have that sharp point right there. Okay, and what does it tell us to do? Zoom in where x is 0. Okay, so we're going to zoom in where x is 0. Hit the wrong button. Right in this area. And what you'll eventually find out is, I'm just going to move my cursor up here, zoom in on that a little bit more. And as you keep zooming in, you're going to find that we are going to be locally linear there. Okay, I'm just going to zoom in again. My cursor was in a good spot. Okay, and you see it's starting to curve now. And eventually you realize that we're going to have a horizontal tangent line right here. Okay. And so therefore the horizontal tangent line is at the point y equals 1. And that's how we get our tangent line right there, y equals 1. Okay. And like I said, you could keep zooming in on this. And the more you do it, the more linear you're going to become at that point. Okay. Let's see if I do this a little faster. But you see it's starting to flatten out more and more and more the more we keep zooming in. Okay. All right. So we use our calculator, and sure enough, we prove that our tangent line is at y equals 1. All right. We're almost to what this all means. All right. If f is differentiable at a point, A, then the equation of the tangent line defines the linearization of f at A. I'm going to explain all this. In point slope form, the equation of the tangent line at the point where x equals a has this format: y minus f of a, that's just y1, is equal to f prime of a, which is the slope, times x minus a, which is the a is just your x value. So there's your x, there's your y, there's your slope. This is point slope form. Okay, linearization is a method of finding the linear approximation of a function at a given point. Okay, this is really what we're getting at right here. Okay, basically this means we can use the equation of a tangent line to approximate values close to a. Okay, once you've approximated the requested value, you may be asked if your approximation is an overestimate or an underestimate. This is determined by concavity. Okay, so over or underestimate is determined by concavity. If we are concave down, okay, so I'm just going to draw a tangent line at some given point. If we are concave down, then we are an overestimate because our line is above our f of x, g of x, whatever our original function is. If we are concave up, okay, so we draw a tangent line here, our tangent line is below our function, so we're going to be an underestimate of the actual value. So now I'm going to wrap this all up and explain what it's saying. Let's just say this is f of x, and we could say it's x squared. It doesn't matter. Okay. Now we don't have a calculator, right? Okay. Think back, 500 years ago, they don't have calculators. Okay. And they have the graph of x squared, and we could do all the whole numbers in our head, right? 2 squared, 3 squared, 4 squared, we know all those values. But if we want to do like 2.251 squared, okay, that's a little harder. Well, if we take this tangent line and this is x equals 2, the actual value of 2.251 on the x-axis, okay, would be, say, here, and we're going to estimate that value by using this tangent line. So I'm going to plug 2.251 into my tangent line to figure out what the actual y value is. Well, it's going to be an underestimate, so I'm going to over-exaggerate here for you, okay? Let's say this is 2.3 right here, okay? Well, the actual value on the graph of 2.3 is way up here, right? Okay, so that y value is a lot higher than this y value, but we're estimating this, okay? And picture this, we've zoomed really far in, right? Okay, so if I want to estimate what 2.5 or 2.3 is, so I want to know what 2.3 squared is, I plug it into my tangent line and it's going to estimate it for me. It's going to be an underestimate because it's below the actual value. And that's because we are concave up. So my tangent line is down here. Okay, I hope that explains it. I'm going to try and do it right here with an actual function. Okay, so you may have thought to yourself at some point in life, I know the square root of 1, and I know the square root of 4, and I know the square root of 9, but how does one find the square root of 1.5 without a calculator? Okay, well, you use calculus and you do this. So let's just type into our calculator. We'll skip 5 and we'll go back to it, but we'll go to our home screen and we type in the square root of 1.5 and it's 1.2247. Okay, we'll get back to 5, like I said. All right, so here is the graph of the square root of x, okay? And 1.5 is right here, right? We have no idea what that value is, what that y value is. It's roughly right about here. What we're going to do is we're going to find the equation of the tangent line at x equals 1. Okay, so the first thing I need to do to write the equation of a tangent line is find my y value. I need a point. So if I have x is 1 and I plug 1 into that, I get 1. That's my point. Now I need my slope. So the derivative of the square root of x is 1 over 2 square root of x. And the derivative at 1 is 1 over 2 times the square root of 1, or 1/2. That's my slope. So I have a point and I have a slope. I'm going to write the equation of my tangent line now. Y minus y1 is equal to m times x minus x1. Okay, there's the equation of a tangent line. And I'm going to try to draw this in as best as I can. I'm kind of just going to make it up a little bit, but let's just say, hopefully that's right there. Let's just say that's when x equals 1. And so my tangent line looks something like this, okay? You don't need to do that unless you want to, but you could just sketch it, okay? Now, think of the graph of the square root of x. This graph is concave down, and it's always concave down. If I'm concave down, my tangent line is above it, okay? And just going back to what this says right here, if I'm concave down, I'm going to have an overestimate, okay? So I'm going to actually use my tangent line right now to estimate the square root of 1.5 by plugging 1.5 into my tangent line. So y minus 1 is equal to 1/2 times 1.5 minus 1. All right, we don't have a calculator, right? 1.5 minus 1 is 1/2. So we have 1/2 times 1/2. So that gives me y minus 1 equals 1/4. And then I'm going to add 1 to this. I'm going to turn it into a decimal, okay? 1/4 is 0.25. And add 1 to that, I get 1.25. So I just estimated that the square root of 1.5 is 1.25. The actual answer is 1.2247. We got pretty close to that, didn't we? We were like less than 0.03 off of that. Okay, that's not bad. Okay, I guess it's not bad. It all depends on how accurate you're trying to be, right? It depends on what you're doing. Okay, so I want to tell you this also. The further I get away from my point of tangency, okay, I start getting into x value of 2, x value of 3 and 4 and so on. Notice how my tangent line is getting further and further away from my actual graph, right? So that overestimate is going to start growing the further I get. Well, you don't want to use this tangent line to estimate every square root. You only want to use this tangent line to estimate square roots around 1. Okay, we don't want to get into estimating the square root of 10 by using this line, because that's just going to get us too far away, right? 10 minus 1 is 9. Half of 9 is 4.5. Add 1 to that, you get 5.5. Well, what is the square root of 10? Okay, the square root of 10 is 3.1, but we just estimated 5.5. Well, we used the wrong tangent line because that one's not good enough for us. Okay, so we would want to use the tangent line. If we're estimating the square root of 10, we probably want to use the tangent line at 9 when x is 9, because that 9 value is a square root we know, and then it's close enough to 10, or a lot closer to 10 than 1. Okay, number 8 here is just saying find the error of your estimation. So you're going to take your 1.25 and subtract the actual 1.2247, right? I'm just going to use my calculator for that. 1.25 minus 1.2247. And remember, 1.2247 is rounded, and I got 0.0253. Okay. Like I said, not bad, not great, but it all depends on how accurate you're trying to be. All right, so number 9 says, what if we use the same line, okay, the same tangent line, to estimate the square root of 1.02? Would our estimate be closer to the exact value or further away? What do you think? Did everybody log out and start playing Fortnite on me, or?
No, sir.
No, just thinking.
All right, it's going to be closer. That is correct. And here's why. Because 1.02 is closer to 1 than 1.5 is to 1. Does that make sense? 1.02 is closer to 1 than 1.5. So this is going to be closer. Okay. If I said estimate the square root of 2, it would have been further away because 2 is further away from 1 than 1.5 is. Okay. All right, number 10 here says use the tangent line from number 3. It's actually from number 6. Okay, scratch that out and say number 6 to estimate the square root of 1.2 or 1.02. Okay, so same thing. We're going to plug 1.02 into the x value of our tangent line. So y minus 1 is equal to 1/2 1.02 minus 1. Okay, remember, again, we don't have a calculator, right? That's the whole point of this, is we're doing this without a calculator. So this is 1/2, and 1.02 minus 1 is 0.02. Okay, y minus 1, mess that up there, is equal to, what's half of 0.02? 0.01. And then add 1 to that, and we get 1.01. So our tangent line is saying that the square root of 1.02 is 1.01. Okay. And remember, we are concave down. Okay. So we know that's an overestimate. So the actual square root of 102 is a little less than this, right? We know it's more than 1 because the square root of 1 is 1. Okay. And we know the square root of 1.5 is 1.2. So we know it's somewhere in between there. Let's get an exact value. The square root of 1.02 is 1.0099. Okay. 1.0099 is the actual. Okay. We're not that far off, right? Okay. So up here, we were 0.0253 off. Now we're 1.01, minus the previous answer. And we're like 0.0004 off. Okay. That means move the decimal 4 places or 5 places to the left. So we're like 0.00004 off. Okay. A lot closer than we were when we did that. Okay. We just keep getting closer and closer. The closer your value is that you're trying to estimate, the closer that is to your point of tangency, the closer your actual answer is going to be to the exact answer. Okay. Because your tangent line is closer to the actual function. The further you get away, the further the distance is from your actual function. All right, real quick, the cosine of 1.5, I think we're going to be doing the cosine one next, is 0.99965. Okay, 0.999. All right, let's go over here. Use a tangent line to g of x equals the cosine of x at x equals pi over 2 to approximate g of 1.5. So what it's asking us to do is approximate the cosine of 1.5. Okay. Remember, we only have 16 values memorized around the unit circle. Okay. One of them is not 1.5. We don't know the cosine of 1.5. We're going to use a tangent line to estimate it. Okay. First of all, I need a point. I have an x value of pi over 2. I need a y value. The cosine of pi over 2 is 0. Now I need my slope. What's the derivative of cosine?
Sine.
Almost.
Negative sine.
Negative sine. Okay, now I need to know g prime of pi over 2, which is negative sine of pi over 2. Sine of pi over 2 is 1, so I get a slope of negative 1. So I got a point, I got a slope. Okay, write the equation of my tangent line. Y minus 0, not going to write it, is equal to my slope times x minus pi over 2. All right, we'd actually need a calculator for that one, right? Because we can't do 1.5 minus pi over 2 in our head. I'm estimating now, okay? So I'll pull out my calculator and I'm going to do negative 1 times 1.5 minus pi over 2. And I get 0.0707. All right, so we know the exact answer because we found the exact answer on this page over here to be 0.999. Okay. We know we're an underestimate. Okay. And an underestimate means we were concave up, right? Because if we're concave up, we're down here, but we got to kind of prove that. Okay. Well, how do we prove if we're concave up or concave down at the point pi over 2? We have to find the second derivative. Okay. So if my first derivative is negative sine x, the second derivative is, what's the derivative of sine? Cosine. I don't know why I wrote it like this in parentheses. I should have put an equal sign. The derivative of negative sine is negative cosine. And we're going to plug pi over 2 into that. What is the cosine of pi over 2?
0.
0, right? So our second derivative is 0. That doesn't really help us, right? Okay. So we'll use our calculator to take a look at that. But let's just graph this right here at, we can do that. It doesn't, we all know what the graph of cosine looks like, right? So cosine starts up here normally, right? But since it's negative cosine, we're starting down here. So it's going to go up like this, and it's going to go up like this, and so on, right? So right here, okay, we're going to turn into going to, right here, we're concave up in this interval, okay? We're concave up, and if we're concave up, our tangent line is underneath. And so we are an underestimate. All right, any questions so far? I know we're kind of moving fast on this today. All right, we'll just do number 12, the last one. We'll skip 13, but it's the same process, right? We know negative 2 cubed is negative 8. We don't know what negative 2.01 cubed is. It's obviously it's close to negative 8, right? But we don't know exactly. Well, again, we use linear approximation to find that by finding our tangent line. Okay, so the first thing is we need our point. Our point is negative 2, negative 8. We need our slope. Yeah.
I have a question about 11. So, like, will we always have to find the second derivative?
Not always. It just all depends if you're given the graph like we were in number 6, right? Okay. And in number 6, we could tell that this graph is concave down the whole entire time because we're looking at the graph. Okay. But and if you know what the graph looks like, you don't have to. Okay. And you know what negative cosine looks like, and maybe you don't know exactly where that point pi over 2 is, but we can see it right here. Okay. But not necessarily. Sometimes you only need to do that if you have to justify your answer. Okay. If you're just estimating, right, on like say a multiple choice question, you're not going to justify your answer. But if you have an FRQ like this next one, you're going to be justifying your answer as to why is it an overestimate or an underestimate, and then you need to find it. Okay, does that make sense?
Yeah, thanks.
No problem. All right, so this one, x cubed, right? We know what x cubed looks like, by the way. It looks like that, right? Okay, the derivative is 3x squared. The derivative at negative 2 is 3 times negative 2 squared, or 12. That's my slope. That's my point. Here's my tangent line. Y plus 8 is equal to 12 times x plus 2. And by the way, you're always going to get a point to estimate or approximate that's very close to your point right here. Okay. We're not going to be getting like negative 3.7. Okay. We're going to get one really close. So it makes this number in here a lot easier. Okay. So the first thing I'm going to do, or next thing I'm going to do, is plug negative 2.01 into my x value of my tangent line. Okay. Now I'm going to solve for y. Negative 2.01 plus 2 is negative 0.01. And negative 0.01 times 12, okay, we're just moving decimal, right? Because this is 0.01, okay? We're moving this decimal that's right here 2 places to the left, okay? So when we move it 2 places to the left, and we're multiplying by a negative, it's going to be negative 0.12. Agree with that? Okay, and now we're going to subtract 8 from that, and we're going to get negative 8.12. We're estimating that negative 2.01 cubed is negative 8.12. Okay, the question is now, is that an overestimate or an underestimate? Is it more than that? Is it less than that? Okay, well, if we find our second derivative, which is actually pretty easy on this function, our second derivative is 6x, and I plug negative 2 into this, I get a negative number, and if my second derivative is negative, I'm concave down, and when I'm concave down, this is an overestimate. So we're going to say it's an overestimate because y double prime of negative 2 is less than 0, or we're concave down. Someone's got their mic on and they're breathing really heavy.
It's like Darth Vader.
Yeah, it is Darth. I think it was Darth Vader. All right, do you have any questions? All right, I haven't put in the curve on your quiz yet from before Thanksgiving, so I will be doing that. I'm going to look at that. I'll look at the numbers and see what I'm going to do with that. I should have that done by Monday. And then next week, we're going to do some practice FRQs, and we're pretty much done. I think we only got like maybe 2 or 3 more lessons, and we'll be wrapping this up. Let me take a look at my calendar here. We have some FRQs we're going to do. We have 2 more new lessons that we haven't learned yet. So FRQs, 2 more lessons. There's a test review in there, and we're going to take a test on all of chapter 3. It might be a 2-day test, depending on where we stand, but and how far we get. I'd like to do it before like the Friday of before we leave for Christmas break, so we don't have to worry about anybody being absent or anything like that. Okay. Do you have any questions? All right, guys. Have a great weekend, and I will see you on Monday.
Thank you.
Have
Have
a
a
good
good
day, sir.
weekend.
Stay safe.
Thank you. You guys too.